in elementary school, we were actually we all wear these lab coats, if you want, but we didn't call them lab coats. School aprons is what we call them. And that is when I began thinking not so much about physics, but I liked math very much, and what I really liked was asking why. In fact, I annoyed several of my teachers because I was asking too much. But my best teachers, actually the ones I remember now, always liked me asking why and always answered and encouraged more questions. My family was always very supportive. We were very close. We were considered a very small family in Argentina. It was just my parents, me and my brother. We, of course, were very close to our extended family. I still go to Argentina every year. I meet with all my cousins, all my aunts and uncles. But my immediate family was very small, but very close. We went every holiday camping together until both my brother, smaller than I, even though he's taller, and I were both in college. We were still going out at least a week with my parents together. And they were actually both college educated in their families. Their families had been very, very economically disadvantaged, so they were first generation college education with the very hard work of my grandparents. My father was an accountant, my mom was a math high school teacher. They didn't know anything about physics. So they didn't very much about physics, but they really wanted my brother and I to go to college, and we got in. My high school was very typical. As I said, I was asking lots of questions. I was kind of nerd in high school, but I still was a girl. My 15th year birthday, that's a very important event in every Hispanic family in the world, I think, not just in Latin America. It's a big party. It was a big party for me, because we didn't have a lot of money, but it was a big event, and I still remember this one. This is a boy I had too. I was kind of nerdy. In fact, I was the best. I had the best grades, and the honor that you have is not giving a speech when you graduate, but carrying a flag in every ceremony, which is actually terrible because you have to be stiff like that for 2 hours at a time, 10 times a year. I didn't like that much. But it was not the popular thing to do, carrying the flag. People didn't come and ask you to be friends just because of that. The other way around, they run away from you. But because I had friends and we actually talked together, by the end of high school, we were very close. And we had recently our 30th year reunion. And it was very nice seeing not just the friends that carry the flag, who were the nerdy ones, but all of the other ones in there. And I'll tell you more about that later. By that time, by the time I was finishing high school, I was very much into math. I was in a technical school that my parents had found in the other side of the city. I had to get up very early to get there. But it was specialized in chemistry. So you would get a chemistry technical degree to be able to work afterwards if you didn't want to go to college. You had a degree. Because I studied more advanced chemistry than in general, I learned about all these atoms and molecules and orbitals, these quantum orbitals, and that's what I liked the best. And my physics teacher was great, and my math teacher especially, she taught us calculus, and I just loved that. So when I had to choose what to do in college, they give you a list of careers, and you have to choose very carefully, because in Latin America, you cannot change majors very easily. You just have to start over if you change your mind. So you want to choose carefully. And I had been watching an ad about doing nuclear physics in another school, away from my city, which is something you don't do in Latin America. You don't go away from my city. In fact, of the 13 cousins we are, there's only 2 of us that have moved abroad, and one has moved to the neighboring country. I'm the one that's survived. So you didn't think about where to go, you just wanted to know what to study. And I thought very interesting time. That was 1983. Democracy was just starting after decades of military dictatorship in Argentina. And the university is a very different organization there. It's a democratic organization. The students have unions, the faculty have unions, and they all elect representatives who then elect the chancellor. And this was all getting reorganized. This, of course, had all been destroyed. Science was also not very well funded. So the whole university, academically and politically, was getting reorganized. And I was very involved in the politics of that. I was just engaged in that, something that made my dad was really afraid. Hello? When I when I started at the university, I realized that there was research being done in the university. There wasn't a PhD program, so I didn't even ask about graduate school or thought about graduate school at the time. There was no graduate school. But there was research for your undergraduate degree. You had to choose a group and do a thesis, a senior thesis. And there was a general relativity group, very active at the time, all men, that I liked to work with. And because I was good at math and relativity could explain lots of things. It wasn't nuclear physics, but it was the universe. It was a structure in the universe. So I started doing that. I ended up doing my senior thesis with Mario Diaz, who was the first person to get a PhD from that program just a year before I graduated with my degree. And there were an active group of people, including some other people like this funny guy who played bagpipes, they're still by, and was doing his PhD research at that university. So I finished that. I did some work. I published my first papers on solving Einstein's equations with a very obscure Russian way of solving equations.
Look at the body's influence on the space they're embedded in. And so in Einstein's picture, a massive body makes a depression in the space-time around it, so that other bodies follow their natural path.
Sorry, this is part of the movie, that's why it has sound. You can find the movie in here. And what I found fascinating about studying Einstein's equation was this interaction between matter and space-time, and realizing that space-time was not rigid, that it was something that was twirly and changing all the time, and thinking that we all lived in this jello that was governed by equations. It seemed to me magical, especially because the equations were very difficult, but still explained things that Newton had explained with a much simpler law, but it also predicted other things that we by now have tested most. So I love the theory. And I don't know that more than anything, but I like to say that I proved, well, not that me and my husband proved Einstein wrong. My husband, that funny guy playing bagpipes, we actually met because we were both doing gravity in his theory. He was finishing his PhD, I was finishing my undergraduate degree, and that's when we started, when we fell in love. So Einstein said gravitation is not responsible for people falling in love. You were responsible. I married more than 25 years ago. We're still very happily married. In Cordoba, and it was a very tumultuous year. I mean, this was 1980. I finished my thesis in 1988. My husband got news of a fellowship to go to Syracuse, New York, and study relativity with a very famous physicist there, Abai Ashtekar. At the time, the gravity group in Syracuse, New York was one of the best, and still is one of the best in the world. Although Abai Ashtekar is not there anymore. So he got this fellowship to go there and study there for 2 years. I was about to start my PhD, this new PhD program in Cordoba. come back and I do my PhD. That was in July '88 when we decided, we said, let's get married first. So we got married in October. Before that, in August, I had gotten a fellowship. The first time I went to Europe, it was with a fellowship to go to a Center for Theoretical Physics in Italy, Trieste, and I developed type 1 diabetes, and I've been taking insulin injections since then, it was a big challenge, and we said, should we still go ahead? I mean, getting married, moving, and we said, yeah, we do it. So we did it. So the same year, I got married, I started taking injections, and I moved from Cordoba, 17 hours away, if you could take a direct flight, it doesn't exist, to Syracuse. So that is a huge change of all kinds. I mean, even in weather, this was February when we moved, middle of the summer, hot summer in Cordoba, arriving during a snowstorm in Syracuse. I can tell you stories about that. Then we got, oh, this is, okay. I'm really sorry. In the PDF, you will see the full picture. But I started a year after we got to Syracuse. We actually decided that Argentina was in very, very bad shape at the time. It had one of the several huge economic crises. His job, his fellowship wasn't even clear that it was going to be continued. And we had actually found this group very, very welcoming and very good in the research that we both were doing at the time. So we decided to stay. I mean, that's not something you decide, you have to get a job too. So he still had this fellowship for another year. I started as a graduate student because I don't know if you all know, but being a graduate student is a job. You get paid to be a graduate student. I didn't know that when I was in Argentina. So I could study while being paid for doing that with this amazing director. But then, again, life throws at you things. And I think somebody talked about the 5-year rule. You should always be thinking about what you want to do 5 years from now. That's about the right scale. I always knew what I wanted to do 5 years from any given year. I was never doing that. I was always doing something better. And that's because life throws at you opportunities and you take them. So anyway, a year after getting to Syracuse, another amazing professor just joined that group, and that's the one hiding in here. That's the graduation picture. That was Peter Solson. He joined as a new faculty. He was an experimentalist, measuring gravitational waves predicted by the Einstein's theory, and involved in measuring those gravitational waves with a project that was being started as a national project called the LIGO project. That was 92, 1992, long time ago. And I took a course with him, a graduate laboratory course, and I loved it. I had done theory all this time. I've never learned to solve it. And I changed. I just switched. I loved it. I had to learn. He taught me how to solder. He taught me how to build circuits. He taught me how to measure gravitational waves. First, in his interview, actually, he showed us this picture. Let's see if I can. Not the picture. That's okay. You can watch the pictures later. He, in his interview talked about these distortions of space-time predicted by Einstein. What they do is not only they make systems, like binary systems, lose energy, something that could be measured by then with radio signals, but they also produce these disturbances in the space-time that travel away from the system carrying energy, and those are things that you can measure. So you can measure here distortions in space-time that are produced by a binary neutron star system out there in the galaxy, farther away. So that was amazing. And you can measure that with an interferometer, just like Michelson did, trying to find the ether. So the idea was that there's this quadrupolar distortion of the space-time, and if you have a Michelson interferometer, then you measure the difference between the travel time of this beam and that allows you to measure the distortion of space-time between this length and that length. Now the predictions are very, very dire. This system of binary neutron stars in our galaxy gets close enough to coalesce once every 10,000 years. So that's too rare, even for astronomers. So you have to look farther. So let's say in the Virgo cluster, where we have a few hundred galaxies altogether, in that volume, these things happen once every 50 or 100 years. How strong are those? They are much farther away. So how strong are those distortions of space-time? Well, the prediction is that this length is going to differ from that length at a few hundred hertz by about a part in 10 to the 21. The prediction is also has this nice feature that it's not how much the mirrors are going to move, it's how much the distance between the mirrors is going to change. So it doesn't tell you this is going to move a nanometer. How much it moves depends on how big this distance is. That's why I'm saying that the prediction is a part in 10 to the 21. Now, if you take as a reference the distance between the Earth and the Sun, a part in 10 to the 21 is 1 atomic diameter. So, measuring these distortions with a Michelson interferometer sounds like a good idea, but technologically sounds impossible. But he said, we've made the calculations and we can make it. We have to be very careful, we have to use a powerful laser, we have to use a long interferometer. It has to be kilometers long, but NSF has looked into this, they are approving, they're building this project. It's going to get done, we're going to get there. I have to say that it sounded incredibly. One of the things that, one of the elements, I'll tell you more about the detectors and how complicated they are, but one of the elements was that these mirrors are not mirrors that you bolt down to a tabletop. These mirrors have to be free so that they are test masses for the gravitational field. You do that, hanging them as pendulums, but even if they are absolutely free, they are still at finite temperature, at least on Earth, so they have Brownian motion. They have this kT of energy in every natural mode, including this natural pendulum mode. So how much that was going to be compared to the 10 to the minus 19 meters we wanted to measure. Actually, this was 4 kilometers long, so this 10 to the 21 converted into 10 to the minus 18 meters. 10 to the minus 18 meters is a part in 1,000 of the proton diameter. So we had to know the Brownian motion. There were discussions about how to calculate that. That was my thesis experiment. It was a pendulum. It wasn't that pendulum. It was a pendulum for the experiment, a torsion pendulum in which I measured the Brownian motion. I converted to the predictions. I extrapolated that by making more calculations, extrapolating that and how it would affect the sensitivity of the detector that was getting built. Now the detectors that were getting built in Hampton, Washington, and Livingston, Louisiana. And I wanted to know what they were. Actually, Jorge and I like taking road trips. We were taking a road trip from MIT, where I was working at the time, and Brownsville, hi Brownsville, if you're listening, where Mario Diaz had joined, my old advisor. So in that road trip, a very long road trip, we decided to stop at Livingston to see what this LIGO was about. This is what it looked like. That is 97, not 95. This is what it looked like. They had just leveled the roads to build these 4 kilometers out. But things happened. Again, with the generous support and very well thought support of NSF, by '99, there was an inauguration of the site, a ceremony held at the Livingston Observatory, in which the civil construction was done and the interferometers were installed. Now, we had to work, and that would be why, but they were there. And these are some of the NSF officers. That was with the Colbert. She was the NSF director at the time, another woman, and Beverly Bircher, who was the Gravity Program Officer. Rich Isaacson was also a person, also a previous Gravity Program Officer that had a lot to do with this. I couldn't find the pictures for you here. So things were happening. Now let me tell you a bit more about where these gravitational waves coming from. Like I said, they are a prediction of Einstein's theory from almost any mass that is accelerated. So I like to say that I'm producing gravitational waves for you here, but if you calculate how strong those are, they're probably not above any quantum level. so the quantum gravity level. So they're probably not measurable. So you have to look out, you have to look at big masses moving very fast. That's astrophysics. So we look at stars living in galaxies. We look at supernova explosions, assuming they are not very symmetric. We look at rotating stars, again, assuming they're not very round. If they're perfectly round, they don't produce gravitational waves. There has to be some quadrupole. Turns out that neutron stars are very, very, very round. So that's not such a good source of gravitational waves unless they're close, but we don't know where they are. So we hope that there's one close enough to see. The most likely source is a binary compact system, for example, 2 neutron stars, or a neutron star and black hole, or 2 black holes that coalesce, and in that last coalescence forming a bigger black hole, or a black hole if there are 2 neutron stars, then they produce these gravitational waves. They have to be close enough, but they could be as far as a bigger cluster for the sensitivities of these detectors that were being linked. So that is one of the most likely sources. You might have heard also about gravitational waves from the early universe. How many people have heard about this news last year? Okay, you. The gravitational waves were on the news, were actually on the newspapers, because it looks like experiments measuring the polarization of the cosmic microwave background, that's electromagnetic background. It looked like there was an imprint in that polarization that had been produced by gravitational waves in the early universe, in the inflationary epoch. So this was a huge cosmological measurement. Turns out that it's not so clear now. There's a component of dust that produces something similar. So how much is dust? How much is gravity waves? We don't know yet. We're waiting for more measurements. I'm pretty sure that there are gravitational waves there. But those gravitational waves happen at all frequencies, so they can be also at least searched for by other experiments. So let me tell you a little bit more about my story. So I did my PhD in Syracuse, looking at how Brownian motion was going to show up in these experiments that were just being built. When I finished my PhD, I went as a postdoc to MIT to work with Ray Weiss. That's Peter Solson, that is my PhD advisor. He actually had worked as a postdoc with Ray Weiss earlier. So in there, I worked with a prototype in which we were measuring some of the techniques on how to use something called power recycling to limit, to lower the quantum noise that limited the detectors. So that was a prototype, and I also worked on the design of the suspensions and the control systems that we were going to use in that initial LIGO. At the time, actually before I graduated from Syracuse, my husband got a faculty position. Before that, he got a postdoc in Salt Lake City, far that way. After that, he got a faculty position in State College, so there were a few years when we were driving every weekend between Syracuse and State College. But then I went to MIT, and that was a bit too long of a drive, 11 hours. Once I made it in 9 hours. So I drove a bit fast. So at the time, what we did was we bought a camper and we parked it halfway, and then we met almost every weekend driving 5 hours each. So that was the There's a story about this in physics some years ago, and they called that a love shack. A few years later, in '97, I got the faculty position at State College. I had an accident driving to that lab shack, so I had broken an ankle. And again, it was winter, and I don't know why good things always happen in winter. So I had to interview in State College with crutches going from one interview to another. It was painful. But they hired me, so we finally shared the same apartment, and eventually bought a house there. I got my first NSF grant. I began setting up a lab to study multiple suspensions and how the suspensions were going to cross-couple and bother the measurement in what we were calling already advanced LIGO detectors, in the second generation of detectors. I was also traveling all the time to Hanford and Livingston from State College. So those were very, very hard years because I was teaching, which I loved. I was setting up my lab, which I loved, with a small group of students, postdocs, and I was traveling to the sites, which I loved. And of course, I wanted to spend some time with my husband too. So some people ask if we have regrets. I always regret not inventing a time machine that expands the daytime. That was hard. But we were happy. And then we were even happier when Louisiana State University offered a very prestigious position to my husband. Remember, he was ahead in the career. He got his PhD at the time I was finishing my undergrad. And that was very close to the Livingston Observatory, which was already beginning to work. This was 2001. So I said, I go with you and I work at the observatory. I'll be a research scientist. Then I have all my time to work on the lab, and that's what I really want. So we were all set to do this, and then I received a call from LSU saying, would you like to consider a position, a faculty position here, an assistant professor position here, which is what I was at Penn State. I said, I don't know, but I'll consider it. I go and talk. So I went, and I said I love teaching. The commute, if I only went to Livingston, was not so far. So I said, I like this. The group of colleagues was wonderful. There was already a strong experimental group at LSU. Actually, they had hired my husband to create a theoretical group, which they didn't have. So we both started as faculties in LSU again. And I loved it. I don't regret that decision at all. Especially because as a faculty, not only I have to teach, I didn't have to set up a new lab. I did most of my research in the big lab down the street at the Livingston Observatory. But I have lots of students and postdocs and lots of parties. Actually, most of these pictures are taken at parties. To the bats of thesis defense and last month. And I love that. I wouldn't have this opportunity to have graduate students and work so close with them. And that's something like that. And they all become my friends. So they're not just your academic family, they are your friends for life. Let me go back to the science. I told you about the LIGO gravitational wave detectors. The initial gravitational wave detectors were built, were operated for a few years. If I have time, I'll show you a few results. And we didn't detect gravitational waves. We weren't expected to because the sensitivity we had was enough to detect these things that happen every 50 or 100 years. So you would say, why would NSF want to do that? Why they would want to spend so much money? It was going to be so unlikely to detect something. And that's because there had always been a second generation thought that would be very likely to detect waves if everything went well. So we were talking about this advanced thinking that saves money at the end. I think, and perhaps Denise and Beverly can say more, but I think that was the thinking, that there had to be some proof, some technological proof that these things on kilometer scale could be done before there was the investment and the technology ready to actually do detections. It was a working lens. And it formed hundreds of people in the meantime. But we are not the only ones. In Europe, we work very close to a British-German group called GEO project. They have a detector called GEO 600 because it is 600 meters long, as opposed to the 4 kilometers long that the LIGO detectors have. And they have developed some of the most amazing technology that the next speaker will tell you something about. We also work very closely with another European collaboration, the Virgo collaboration, that operates a 3-kilometer detector in a beautiful region near Pisa. And there's also a detection under construction in Japan, which is an underground detector. And there is also, there used to be a plan to house 2 detectors in the same observatory in Frankfurt. Now, one of those detectors will be housed in an observatory in India that will begin to be constructed very soon. So, in a few years, the worldwide detection network will not be just LIGO. We do have a network, a worldwide network. And somebody said earlier, physics is now global. And it is true. You collaborate, you don't just talk, you collaborate, you meet colleagues all over the world in all kinds of technologies to help you on these difficult projects. Marco mentioned the LIGO scientific collaboration. That's a collaboration that grew to do the science with these LIGO and GEO detectors. We have more than 900 members in more than 8 institutions in 16 different countries. About half is in the US, about a third is in Europe, but we have smaller groups in many, many places, including Australia and now larger groups in India. So we need a lot of structure to make the science happen. And we need some people directing that structure. We don't pay anybody, so we cannot tell anybody what to do. We have to convince everybody that what we need them to do is good for everybody. So it's a different style of work than in most other places. But we do it. We say, I'm the cat herder, 900 people cat herder. But we have done very, very good things. This is a plot showing the sensitivity, one of the ways of showing sensitivity of the LIGO detectors, the best they were up to a few years ago. So what I'm showing here is a plot of noise versus frequency. The units for the noise are strain units. Remember I told you that Einstein predicted that gravitational waves would produce not distance motion, but changes in distance for the baseline. So this is the change in distance over the 4-kilometer baseline, and therefore it doesn't have any units, except that because you're looking at the density, then you have to divide by square root of currency. It's like the square root of the power in each frequency band. So this is the noise as a function of frequency, and because it's a noise that doesn't let you see a gravitational wave of an amplitude that's larger than that noise. So you want that noise to be as low as you can. You want to lower the noise. This black line was the design sensitivity. That was what in the 70s already, but formally in the early 90s, people promised NSF the sensitivity could be with these LIGO detectors. And you can see that it was even a bit better than that. Now look at the numbers here. I told you part 10 to the 21. This is 10 to the minus 21. It is a density, so you have to integrate the noise. For example, if you have a gravitational wave at 100 hertz, then you want to bond the noise in a frequency bound around 100 hertz, so you have to integrate. So the integral over the 100 hertz band here is 10 to the minus 21, even though these numbers look a bit lower. It's a bit lower than 10 to the minus 21, but that's about the round number. Now, what makes this noise, and how do you make it smaller for advanced LIGO? Well, that's a lot of thinking and technology. moving, the mirrors and the pendulums moving due to the ground moving. Even though the pendulum actually mimics the noise at these frequencies, but also we have lots of seismic isolation, the mirrors still move a little bit. But because of all those pendulums and seismic isolation, the motion decreases with frequency very, very quickly. So we are limited by seismic noise at these low frequencies. At these high frequencies, we are limited by the quantum noise in the lab. We use these laser split to go back and forth and measure these distances. And laser is made out of photons, and your photodetector is looking at photons, it's counting photons, and it has an uncertainty in how many photons there are. That's, in engineering, it's called the shot noise. But it's actually the quantum noise. And when you want to calculate the noise at all frequencies, it turns out that you can reduce the shot noise if you increase the laser power, but if you increase it too much, you begin pushing the mirror. And then that is called radiation pressure noise, and that's the other side of the Heisenberg principle applied to this experiment. So it's all quantum noise. So we are limited by quantum noise in here. And in the center, we were limited by several different things, but we couldn't go much farther than that because of the Brownian motion I told you about. Now, the pictures I have in here was research that was being done while this detector was being built, so that an advanced detector could be built that would detect gravitational waves because it would have lower noise than this. And the way that was done is with much more sophisticated seismic isolation, with multiple pendulums instead of a single pendulum, with state-of-the-art polished optics that are hanging not from metal wires, but from glass wires, from fused silica wires that reduces the Brownian motion, higher power lasers, more complicated optical configuration. It's not just a simple microphone, and I could give you an hour's talk on what all these mirrors are. And just to trick up your sleeve for the future, and part of the next talk, you could also, if you wanted, and we have proven this is possible, you can manipulate the quantum noise to make it smaller at these frequencies at the cost of increasing it at these frequencies. But at these frequencies you have other noises, or the other way around. So this can be done. It has been done with a limited phase. It's not something we are installing to do just now, but we can do even better. It's not only the noise that you have, it's also how you analyze the data. The data that you look out of the detector looks like noise. In fact, it doesn't quite look like noise. It often has large transients in there, and you say, those are the waves I was looking for. Except that they happen many, many times a day. And they only happen in one of the observatories and not in the other. So you know they are not as of physical origin. Those are glitches. So we do a lot of work on not just calibrating the data, but cleaning it up from these glitches. But then we also analyze looking for different signatures. We look for, this picture doesn't show very well, but these binary systems produce sine waves that increase in amplitude and frequency as these two stars move closer and closer together until they coalesce. When they coalesce, there is a ring down, and then there's a decay of the gravitational wave. So there's a specific pattern to look for. For rotating stars, there's also a very specific pattern. It's a sine wave. For the cosmic microwave background, that's very tough because it just looks like noise. In fact, I just calibrated it as noise. But the way you look for this is looking for correlations in the noise between two different detectors. So it's in the cross correlation how you look for astrophysical outcomes. And then there's looking for the unknown. When you look for the unknown, you don't use models, you use some signal analysis techniques, wavelets, things like that, and of course that would be the most exciting discovery. You can translate a spectrum like that, a spectral density like that, into how far you can see certain signal if you know what the signal is. So for example, if you talk about binary neutron stars, then given a spectral density, we the system was just aligned with your detectors. But in average, how far you could look in megaparsecs as a function of year. So we took data for 2 years with 3 LIGO detectors, one 4 kilometers long at Hanford, one 4 kilometers long at Livingston, and another 2 kilometers long at Hanford. And you can see that this one doesn't see as far because it's not as long. You are limited by what your displacement sensitivity is, but when you want to translate that into gravitational wave, you have to divide by distance. It's not in nanometers, it's in strain when you need to measure. And if you divide by 2 kilometers, you get twice as much noise than if you divide by 4 kilometers. So this shows that length really matters here. And this was about the Virgo detector in Europe that used slightly different technology. We stopped for a while when advanced LIGO was funded, but that technology took a while to get ready to install, so there was the installation of some of that technology, and then there was another data taking run for about a year. You can see that the reach was actually better. This reach is about the Virgo cluster. The Virgo cluster is at about 16 megaparsecs. That's about here. So we were sensitive to these signals that happen once every 50 to 100 years. We took data for a year. What did we see? Well, you haven't heard about discovery of gravitational waves, so you know we didn't see that, but we saw some interesting things. In 2007, there was a gamma ray burst that was localized apparently near Andromeda. And Andromeda is only 1 megaparsec away. So if gamma ray bursts, those gamma ray bursts had been produced by a binary neutron star system, which is the favorite model, in Andromeda, we should have seen the gravitational waves produced by that, because 1 megaparsec was well within the sensitivity of our detector. And we didn't see anything. So we could rule out a binary neutron star system in Andromeda as a source of that GRB. Of course, it could be a binary neutron star system in some other galaxy behind Andromeda, or it could be something else in Andromeda. But measuring zero, Denise was talking yesterday about measuring zero, sometimes is very important. And then in 2010, almost before finishing in September 16, we saw a very, very interesting signal. And I won't tell you more, I'll leave that for questions if you want, but that was the best thing we have seen so far. And it was a clear detection. Except it wasn't. Again, I can tell you the story in questions if we have that. So, what will advanced LIGO see? So this was a design curve for initial LIGO that was achieved. This is a design curve for advanced LIGO, 10 times lower noise, which means you can see 10 times later, and this picture was first produced by the converter, which is the program office that advertising this. With this sensitivity, we could see about 15 megaparsecs away. We expected to see these binary systems once every 50 years or so. With advanced LIGO, at its best, which takes a while to get there, we'll reach about 200 megaparsecs. With that sensitivity, we expect to see tens of signals per year. Now, astronomers put their error bars in the order of magnitude. So that 40 signals per year could be 400, but it could also be 0.4. But that just means it's a matter of year, because these are small numbers, but not that small. So it's only a matter of time that these signals will come. And if you ask me, I think they will come earlier rather than later. There is a lot of support for numbers like this. And then there are other systems, like neutron star black hole systems, black hole systems, and of course all the unknown. And those all should add up. Of course, making predictions is always difficult, especially about the future, said Niels Bohr. That is always attributed to Yogi Berra, but I think Niels Bohr said the same thing before. Okay, so when are we going to get there? That's the other question. Are we there yet? That's what we asked always my parents going on these family vacations. And we're there yet. And they always said, we're almost there. Even from the beginning, they said, we're almost there. So I'm saying soon, but I'm going to quantify that and say how soon. This year, 2015, we plan to have the 2 LIGO detectors working with the sensitivity, not the 200 megaparsecs that we were talking about, but somewhere in between 40 and 80 megaparsecs. And physicists are usually optimists, so we try to be realistic here, but I should tell you that the Livingston detector has achieved already 50 megaparsecs in these units. So we are already above the expectation in at least one of the detectors. And we think that this one will happen sometime in the fall. So we are getting there. Now, with that sensitivity, we plan to take data for about 3 months. The expectations, taking the worst possible, well, the worst expected sensitivity times the worst expected astrophysical rate is 0. The most optimistic value will run at 80 megaparsecs, 2 detectors, 80 megaparsecs, and the most optimistic astrophysical estimate is right, which never is the case. It would be a few. So it's not impossible. It could be happening this year. I wouldn't bet a lot of money though. But next year, detectors will improve. We think that there will be around 100 megaparsecs. Virgo will start taking data. Virgo is about a year behind, so we will have 3 detectors that helps your sensitivity. And with that, again, the lower limit is 0, but the upper limit is 20. The realistic number, you have to divide these by 10 or 20. So it's there. I have my hopes high for next year. That will be a run of 6 months, although of course all these predictions go out the window once we have a detection. But then in 2017, we think that the LIGO detectors will be at about 150 megaparsecs, the Virgo detector will be around 70 megaparsecs, so that, for sure, if we haven't seen before, we would already be seeing several signals or setting very, very strong upper limits on the astrophysical predictions. Of course, that's not what we want to do, but we would already be learning. Now, if you keep going, the lower limit per year is not 0 anymore. It's just close to an integer. So it's only a matter of time. This project started in the 70s with Ray Weiss started thinking about using interferometers to detect gravitational waves. It's 40 years, it's going to be almost 50 years since it all started. He's still coming to Livingston to fix photodetectors and check the vacuum system and help with the latest problem, but gravitational waves are here. Now, before I show you the gravitational waves are here, I want to say that my life in physics has been following this dream, although I changed paths a few times, as I told you. But it's not all about physics. It's about family and fun and putting it all together. Some of my hobbies are, like I said, driving sports car, knitting, visiting family. These are, I don't have children, but my brother has 3 children, and I never spend enough time with them. This is me knitting. I always take some new clothes for them. And many other pictures with friends and family, many colleagues, many students. It's all about putting it all together. It's all being happy and having fun while we do physics. So let me end with that saying, life in physics is fun. If it's not, you need to change paths. You can change paths. You can be in a different place that you thought you were going to be 5 years ago, and again, it's going to be better. So let me end telling you also that if you want to learn more about LIGO, go to LIGO.org, and I hope you ask me a lot of questions now, and if you don't have time, email me, find me later if you're here, or if you are at the other institutions, please email me. Thank you. disappointed if I don't have questions.
Yeah, I can believe that you don't have questions. Here.
All right. Thank you. Can you please tell us what
Hi, is it open for questions, or are you going through sites? We couldn't hear the last minute.
Oh.
Okay, all right. We are going for one question here and then we'll open it to the other side.
I don't know if you could hear that. Marco said we're going for one question here and then we'll open to the other sides. So there's one question in the back.
Can you please tell us that interesting discovery you guys had that you had to skip over
I'm
first
sorry?
time? The interesting discovery you guys had that you weren't going to share.
Yes. We actually saw a very interesting signal that was a very strong signal in Hanford and Livingston, not very strong in Virgo, but Virgo was less sensitive, so it makes sense. And we spent a lot of time analyzing it, convincing ourselves that it was real. There were some strange things about it. We called it the big dog because with 3 detectors we could kind of triangulate, and it was near Canis measures, so we called it the big dog. And then before we wrote a paper, a discovery paper, actually said evidence for detection. But we wrote a paper about this event, but we had promised, and we remember that before sending the paper out, we were going to ask the project director to open an envelope to say whether that had been a blind injection or not. We had agreed, actually in the last 2 science runs, in all that data taking that you saw there, that we asked a small group of people to test the whole discovery process, injecting, if they wanted, some signals that they chose at some time without telling anybody else. So this was done in coincidence, so this signal was injected, could be injected in 3 detectors. We had done this exercise in the first run in S5, that's 2006 and 7. We missed one of those injections, which showed that we didn't have very solid procedures. There was another that was marginal, and we discussed it for months and months, and we decided that wasn't worth publishing on its own. In 2010, we saw this one, we were ready to publish, but it was a blind injection.
Oh.
But we proved we could find it. And we learned a lot of things. That's actually not so rare in experimental physics. We learned it from other experiments too, and it was very, very useful. We plan to keep doing it.
Okay, so I lost track of who is who. So, remote sites, if you have questions, unmute yourself, introduce yourself, and ask the question. First serve, first come.
Hi, I'm Grace Mumby at the Rutgers conference, and I'd like to know how an interferometer works as a gravitational wave detector if the beam is redshifted by the passing wave.
That's a very good question. It is true. It is true that the actual electromagnetic wave also gets squeezed or stretched in the arms, similar to the stretch and squeeze of the 4-kilometer distance. However, what you measure in an interferometer is not how long the wavelength is. What you are measuring is the difference in the time the photons take, or the wavefronts if you want, to go out 4 kilometers and come back. An assumption in the theory is that they travel at the speed of light. They both travel at the speed of light. The beams might change wavelength, but they do travel at the speed of light, both. So they might get a bit red shifted and blue shifted, but they will travel at the speed of light, and you start with the same wavefront. They travel away, they come back, and they will not find themselves in the same place than they departed. So there will be an interference signal, even though your calibration, which is the wavelength, will be off by a part in 10 to the 21. But we are struggling to get calibration to the few percent. So it's a good question, but you have to think about not measuring the wavelength of the beams that are traveling, but how long the wavefronts take in travel those distances that are different. Thank you for the question.
Other side? Any questions from other side? Rutgers, then go for a second question.
Hi, Dr. Gonzalez. One of the questions over here is, how do you suggest that students who don't have gravitational wave physics programs at their university get involved? And also, on a day-to-day basis, is the nature of the work more theoretical or more experimental?
Well, the answer to the first question is find summer research. There are lots of summer research opportunities in the US. There is this fantastic REU program, Research Experience for Undergraduates. There are several universities that do gravitational waves, including Caltech and MIT, but also LSU and others, that offer these summer opportunities to do research on gravitational wave detection. So that's the best way to get involved and see if that's what you like or not like. Somebody says it's important to try different things because sometimes you like some things better than others. The second question was, I forget now. Oh, whether it's more important to have a theoretical or experimental background. We do everything. As you saw in the detection of gravitational waves, we do a lot of signal processing, and for that you have to learn about the waveforms and general relativity and modeling those waveforms on computers and finding those waveforms in the noisy data. So you sit in front of a computer, essentially. So you don't need a lot of experimental experience, except that you always want to know what the experiment is about. But there are also people who do a lot of hardware. You always have to touch computers, but in those cases are to control the instrument without doing much analysis of the signal itself. So we do from the basic experimental research on future technologies, applied technology to the detector, signal processing, signal modeling, not inside the collaboration, but in general, in the gravitational field in general, there are lots of other groups working on numerical relativity, producing the waveforms that we will detect later, and that will be important in order to interpret the discoveries that we have. And there are people also working on mathematical relativity, still understanding in different ways and making predictions with Einstein's theory of gravity. So within the LIGO collaboration, we do a lot with data processing, waveform modeling, and experiment. So almost no matter what you like, you can find somebody to work with. But if you are more theoretically oriented than that, then there are also lots of gravitational wave research done outside our immediate LIGO collaboration that has to do with gravitational waves. I hope that helped.
Any other questions from other sides? Okay, so Yale says Yale has no unanswered questions thanks to Dr. Gonzalez. Rutgers, one more question.
Hi, this is Catherine Sparks-Little. I'm actually a grad student at Penn State. And my question regards being the spokesperson for such a large collaboration. What are some of the biggest challenges that you faced and suggestions for people who join large collaborations?
Well, joining a collaboration is not the same as leading or leading one of the groups in there. So let me answer first your last question. If you want to join a collaboration, make sure you like to work with people. Because you will be working with a lot of people, some that you like better than others. We work together a lot. He's assistant spokesperson of the collaboration. But also we use a lot of remote technology, so we are in touch with a lot of people that are not around you. You talk to them every week, you call them up, you Skype them every day, almost every day if you need to. So we use a lot of these remote collaborations. So the good thing about that is that you have help, no matter what your problem is, if you ask for help. But you need to know how to ask for help, and you need to like working with people. But on the other hand, I think the environment, at least we try to make it friendly, we find ways to help newcomers. It is a bit of a challenge. It is to go from a small group to a large collaboration. Now we have collaboration meetings, we have hundreds of people there, but we organize things for the younger people, especially, and for the new people who are not always young, to learn the ropes. About leading the collaboration, well, it's a matter of convincing people that you have good reasons for people doing what you need them to do, and what's harder, convincing them that they have to do it on time. So it is hard. I have learned a lot doing it, but it is a very rewarding job too, because you see progress. I see the papers that we publish, I see the exposure that we have, I see people being excited about what we do, and thinking that you are part of that, an important part of that, is very rewarding. Thank you for that question too.
Maybe we can take some questions from here. We don't want Raptors to win. 3-1.
They both another question.
Oh, I was also going to ask about the story, but you can do that. How, if at all, has being bilingual influenced the opportunities that you've had in your career, and would you recommend that students pursuing a science degree learn another language?
Coming to the US was a challenge. I had studied English in Argentina for many years, and I thought I knew. I mean, I had gotten good grades in my English exams. I had a degree from the British Academy. Nobody could understand a word. I mean, I still have that, like you heard, a very strong accent. So languages are not it's not a skill I easily have. But it has been very useful, not so much to learn another language, but to learn another culture. Learning how different things were in the US and in Argentina made me think about how broad cultures can be. And what things I thought were good, people didn't care, and things that I thought were okay, people thought, oh, that's so good. That kind of experience, which is related, but it's not to language, but to culture, is very important. And that was also very nice in graduate school. In graduate school, I had classmates from many different countries, and I loved that. I mean, learning so much about what's so different and so special in so many places. It's an experience that opens your mind, which is what you want your mind to do, because in science you need a very open mind to come up with new ideas. So I would recommend travel, be open, get to know people from other places, more than learn other languages. That's useful too.
Yale has a question. Go Yale.
Yeah, go ahead, just speak up.
So last semester in physics, we learned about how using spin squeeze states can decrease the photon noise limit of LIGO and improve the resolution. Can you explain, like technically wise, how exactly do we prepare these spin states?
Yes, well, I'm not the technical expert in that, and it's a pity you're at Yale because we have actually a talk about that following this one here at our meet. But essentially, the laser beam is a coherent state. If you have taken those courses, what a coherent state means is that it's a state with minimum uncertainty both in position and momentum. So you cannot know exactly where the wavefront is and what the wavefront is, but you have minimum uncertainties in both of those degrees of freedom, which you can translate into amplitude and frequency. And so when we use these coherent beams in the detector, that's the uncertainty that you have, the uncertainty that you have in the coherent beam of the laser. Now what you can do is make that, another way of explaining that, and again, I'm stretching outside my expertise here. The actual calculations that were done by Case in the 80s, I think, early 80s or late 70s too, is that uncertainty is produced by the vacuum uncertainty. So that uncertainty, even if you have a laser with zero amplitude, with zero power, you still have the vacuum uncertainty, and that's what produces this measurement uncertainty that you have. So what you can do is prepare, and this is going to sound magic, but it actually exists. You can prepare a squeezed vacuum state. So instead of having the regular vacuum, you produce a vacuum state, which is a laser that goes through a nonlinear medium to make these uncertainties be different in the 2 degrees of freedom. But then it's like turning the laser power to 0. So you still have that uncertainty, but now it's not the regular vacuum uncertainty, it's a squeezed uncertainty. And it's an interaction between that squeezed vacuum with your measurement would produce a better way of measuring the degree of freedom that you want. Of course, you can make it worse if you choose the wrong degree of freedom to squeeze. And one of the challenges now is to make that squeezing different at different frequencies. Because if you squeeze amplitude, you get better at low frequencies. If you squeeze frequency, you get better at higher frequencies. What you want to do is do both. So you can squeeze differently the vacuum at different frequencies. And that, again, I know it sounds like black magic, but you actually go to lab and see done. It was done in the Hanford detector, used squeezed vacuum to improve its sensitivity before we turned it off in 2010, and it worked. I know it sounds obscure. If you read our articles in LIGO.org, there are some references there that can help. It's magic. Physics is magic. That's very nice.
We still have a few slides. 1, 2, I lost track with. I think this one is open, but I'm not sure. Any other questions from any other side? We still have about 10 minutes. So, yes. Okay, we go for a question here.
I was wondering if you've ever struggled with imposter syndrome or anything of that nature. If so, how did you get through that?
I still do. For people who don't know what that is thinking you don't deserve to be where you are, that you got here just by luck, or and that you are not as good as people think you are or tell you that you are. And everybody struggles with that, not just women. I have known many people struggle with that myself. I catch myself thinking that a lot. And you just go back to why is it that you are what you are. And when you go back to the facts, it's not luck. I mean, there might be luck involved, but you need to take advantage of opportunities. Opportunities appearing, that happens more often than people think. Not taking advantage of opportunities also happen more than people think. Taking advantage of opportunities is not taking advantage of the situation or taking advantage of other people. It's not, even though sometimes we think that way. So it's going back to the facts. You are what you are because you worked hard, because you did your best, and also when you feel, when something doesn't go right, you did your best. So that's all you can do, and you should be proud about that.
What is the representation of women like in your collaboration?
Not as good as we'd like. It's about average in physics, but of course that average is not what we want to be. I wanted to mention something I forgot. When I got to LSU, like I mentioned, it was, I mean, they actually asked me to apply. Of course, there were other people interviewed. I found the colleagues very, very friendly and close. When I, shortly before getting there and shortly before accepting the position, I realized I was going to be the first tenure track faculty at LSU in 2001. There were a few research professors and instructors, but no tenure track faculty. I thought, how can that be? I mean, I know situations like that. Turns out that there are many, many institutions that still have one or no women. So, you know, when numbers are small, fluctuations are large. But I didn't feel, going back to the imposter syndrome, I could have thought, oh, they just want me because I'm a woman. And that crossed my mind. But it wasn't, and they didn't make me feel that way. I knew it wasn't because of that, and it wasn't, and it's all been good. In the collaboration, we have about 20% among the younger people. I think we counted. Marco is the chair of the diversity committee. We have a diversity committee. We have about 16 or 17% about more senior people, which again is about average. We have made, we are making a lot of effort to increase these numbers. We are doing that mostly by increasing the climate for everybody. Working on the climate to make it friendly, to make it easier for people to start, for making it easy for people to stay, but also having policies for people feeling free to relate their experiences. We have created the ombudsperson position, which Beverly Berger here has kindly accepted. So they have, people have somebody to talk in confidence if they want to, which doesn't involve their advisor or the spokesperson, and that has worked well. We have instituted an anti-harassment policy. It's not a sexual harassment policy, it's anti-harassment policy. And it's not about only about harassment of women, it's harassment. Nobody wants to be harassed. making life better for everybody, what we think works best. It takes decades to change these numbers, so it's very difficult to say whether these activities are working or not. But we do have a very strong working group on diversity that Marco chairs, Marco Cavaglia here. We also try to involve men in all of these activities, because increasing diversity is not a job that only women should do. You often see all these diversity committees and groups with just women. It's not quite right. In our collaboration, there are many colleagues, male colleagues, interested in increasing diversity. That's very good to see.
All right, thank you very much for the talk and the Q&A session. So we have now a group photo schedule. Okay, it has outside, I think.
Well, thank you to all the groups for participating. I don't know if you have signed off, but thank you all for listening.